we're going to talk about Advanced Hydraulics 2. Now notice the subtitles here are Cavitation and NPSH. Advanced Hydraulics. Two questions you got to ask yourself is, what's my flow rate? What's my total dynamic head? All right? Total dynamic head is made up of two things. It's made up of your suction head. Notice that it says suction head is made up of static suction lift. That's the vertical distance from the datum plane of the pump to the surface of the water. And I'm going to say the working surface of the water. Okay? It's made up of suction side friction loss. So in other words, how much friction loss is going to be caused by the size of the pipe that I'm using. And then, of course, drawdown. All right? Drawdown is the working level of the water. So if I turn that pump on and it draws that water down, there's my working level. That's the number that I need. So static says from wherever the highest point is to my datum plane, and then drawdown says, okay, we're going to go from the static level down a little bit. On the discharge side, we've got static discharge head, which is elevation. It's measured from the datum plane to the highest point I have to pump the water. I've got my discharge side friction loss. I expect to have a little more here, but still I get real concerned if someone comes in with a really high friction loss. Okay? Keep the friction loss low by upsizing that pipe. And then lastly, my head or pressure requirement at the point of usage. And it depends on what you're doing. If you're running a sprinkler, the point of usage is the sprinkler head, and I need 40 psi. Okay? Now, this is a pump curve here, and there's actually 4 curves in one. All right? The title of this, and if you're following along, this is on page 11 in the Water Systems Training Manual. The title of the page is Net Positive Suction Head, NPSH. There are 2 types. There's NPSH-A and NPSH-R. We're going to talk about R. Okay? R means the amount of head required by the pump to keep the fluid in a fluid state. All right? Now, the first curve we're looking at here is the power curve. Notice it's red over here in horsepower, and it's at an angle like that. The more water I flow, the more power I need. Okay? Then there is my head and flow curve. That one runs here. And again, you'll notice that as my flow goes up, my head comes down. Okay? The efficiency curve, which is red over here in percentage points, and you can see it goes up and it makes a high point. When I go right straight across on that high point, my guess is going to be 62 feet ahead at that point on my curve. All right? And then lastly is NPSHR. NPSHR is red over here, and I go right straight across from where that flow rate that I picked crosses that line. I'll be at about 18 feet. Okay? So, looking at each individual one, flow and head. That's what you're looking for here. You're looking for flow and head. We chose a rate of 87 gallons a minute. You'll see why we did in just a little bit here. Our head is going to be 130 feet. Okay? So as your flow goes up, your head comes down. As your flow goes down, your head goes up. That's the way a pump curve works. Okay? Now, the next curve we said was going to be our power curve. It's horsepower. It's red over here. You can see this one has a max of 5 on it. The next thing we're going to do here, we're at 87 gallons a minute. Remember, we go right straight across from where 87 gallons a minute hits that power curve, and we're right about 5 horsepower. Notice what happens, though, if we do a shut-off head test and bring that flow down to 0. Now, the formula says gallons per minute times TDH times specific gravity divided by 3960 divided by pump efficiency equals my brake horsepower. The specific gravity of fresh water is 1. 1 times any number. You can see why I don't put specific gravity in there very often. 3960 is a constant. The way that you get to 3960, you divide 33,000 foot-pounds per minute by the weight of 1 gallon of water, and that's going to equal 1 horsepower. So 33,000 divided by 8.334 equals 3959.68, and it gets rounded up to 3960. That's where that number comes from. All right. So the more water I flow, the more horsepower I need, and obviously the opposite is true also. Something else too important though. So the more water I flow, the more horsepower I need. At 10 gallons a minute, that means that I would need 83.34 pounds of water that I'm lifting. At 100 gallons a minute, I'm lifting 833 pounds, 0.4 of water. And at 1,000 gallons a minute, I'm lifting 8,334 pounds of water. Okay? As my flow goes down, my horsepower requirement goes down. So you'll notice here that at zero flow, we're at about 2 horsepower. So, what is one way you can tell the horsepower of an electric motor? Most people know you call it amps. Okay? So, of course, what that means is as your flow goes up, your amps are going to go up, and as your flow goes down, your amps should go down. BEP stands for best efficiency point, but what does it really mean? So let's take a look here and see. And you'll notice here it's taken on the right-hand side of the curve. There's my efficiency point. And what we're looking at is where the flow rate that I picked of 87 gallons a minute crosses my best efficiency point curve. So where I cross that curve happens to be at the zenith. All right? And I'm at about 62%. Now, best efficiency point. What it really means is this. We want you to stay within 5% of that best efficiency point. Now, we can't be talking up or down because up or down means that's not my best efficiency point. So, best efficiency point means 5% on the high side of the flow of my best efficiency point or 5% on the low side of my flow for the best efficiency point. Now, what does it mean? It means if I take 62 and I subtract 5, I get 57. Draw a line right across 57%, and you can see you're crossing that efficiency line twice. Once on the low side of the flow, once on the high side of the flow. So, what is the flow range over here at the low side of the flow? We'll call it 55. And over here on the high side of the flow, we'll call it 120. All right? So what does it mean? It means that my pump operates most efficiently between 55 and 120 gallons a minute. That's what we're telling you. Okay? Now you'll notice that you can go less. I had a guy call me up one time. He wanted to do 40 gallons a minute. But you'll notice at 40 gallons a minute, we're only 57 or 50% efficient. All right? What if I go out here to 150 gallons a minute? Now I'm only 38% efficient. So you're more than 5%. Watch that. That's what you're looking for. Okay? Another way. So the curve that we were looking at was out of the Beck 2 program, which is our Berkeley Big Iron. Now we're going to take a look at our S4500 WS. That's the Stay Right Water Systems catalog. And this is obviously the PD series pump. Okay? You'll notice there is your curve, and the curve says recommended operating range. That curve crosses through each one of those pump curves twice. Once on the low side of the flow, once on the high side of the flow. So you'll notice that 2.5 horsepower, somewhere between 78 and 24 gallons a minute. When you go to the 2 horsepower, now you're between 66 and 21 gallons a minute. The 1.5 is 64 through 18 gallons a minute, and the 1 horsepower is 52 to 16 gallons a minute. So that's what we're going to recommend, that you work within that range. Now, NPSHR. It stands for net positive suction head, and remember, it's the amount of head required to keep the fluid in a fluid state. It's read over here in feet of head. All right? Now, at 87 gallons a minute, we cross the NPSHR line right there, which puts us at about 18 feet. And it's saying, I want 18 feet of head to keep this fluid in a fluid state. In other words, how much head back pressure do I need to prevent cavitation? All right? So, if we take that 18 and we subtract it from 25, that leaves us 7. 7 feet to do what? 7 feet to design the suction side of the pump. So now we can say, okay, the suction side of the pump, remember we just learned in the last one, the suction side of the pump requires two things. It requires my vertical lift, but it also requires my friction loss. Those are the two things I need. Okay? So, since friction loss and vertical lift make that up, that means that if I've got 3 feet of friction loss, I can only be 4 feet above the water. Really important that I understand that. Now, of course, remember, we're going to go low at 55. We're going to go high at 120. But notice that if I go low to 55, my NPSHR drops to 16. If I go high to 120, my NPSHR goes up to 22 feet. So it goes up to 22 feet. That gives me just 3 feet. Gives me just 3 feet. So you have to decide, and you have to make some decisions here based on this information. That's why it's so important. Now over here, back to this real curve, I want you to understand that this sometimes gives people a little bit of edge because they can't tell how many feet of head there is. Okay? So here we've got our 2.5 horsepower curve. Our shutoff head is about 142. What that 142 is made of is, let's say, and now if you look down the lower left-hand corner there, you'll see a gray line went right over the red line. The gray line represents the vertical lift. All right? The green line there represents the pressure that's left. And if I change my vertical lift, I change the amount of pressure that's left. All right? So, again, remember what we said, as your flow goes up, your head comes down. And you can see that's true. Okay? Now, the other thing that it means is this. If you look at the curve there, you'll notice the dotted line. The green line moved from all the way out to the edge down on that dotted line. And that's because I had 15 feet of lift. At 15 feet of lift, I can no longer hit that point on the very end of the curve of 78 gallons a minute. It's really important you know that. And if I go to 25 foot of lift, watch what happens now. It's going to change even more. Okay? So I look at 25 foot of lift, and we're running, 62 gallons max? And you're probably cavitating at that. All right? So, this is the box chart. It's right above the curve itself. All right? There's your 1 horsepower, 1.5 horse, 2 and 2.5 horsepower. Right below that it says distance above water. Now remember, that includes vertical distance, but it also includes friction loss. All right? Each one of these box charts have 5 to 25 feet. That's because most people consider 25 feet to be the maximum lift of a centrifugal pump. All right? On the left-hand side of the curve there, it gives you your flow from 10 all the way to 50. If we want to do 15 feet of lift and 30 psi, all right, you can't mix psi and feet of head, but if you change the psi to feet of head, now you can do it. So 30 psi times 2.31 is going to be almost 70 feet, plus 15, that's 85 feet. Notice what it says we should get for flow range, about 27. So we come back to our curve. We put a line in here at 87 feet. We find where that 1 horsepower crosses that 87 foot line. And where are we at? Yeah, about 27 gallons a minute. So that's pretty accurate. Now, the next thing we're looking at here is the formula to calculate NPSHA. Remember, A is what's available to me on the suction side. So we've got PA minus PV plus or minus Z minus F equals NPSHA. So PA stands for the pressure or gauge pressure in feet of head, because we always talk about pressure in feet of head. Okay? PV is the vapor pressure point of the liquid. At which point will that liquid flash from a liquid to a gas? Z is the static height above or below the datum plane of the pump. That helps me to know if my water supply is above or below the pump. F is the one most people have problems with. F stands for friction loss. Most people don't take friction loss on the suction side of the pump into consideration, and sometimes that can really cause you a lot of problems. All right? So this is the vapor pressure point of water at various temperatures. And basically what we're doing here is we're saying, okay, so if you've got this much pressure over the water, that water is going to flip from a liquid to a gas. So at 212 degrees, 14.7 psi, which is sea level, you can boil water at around 34 psi. I bring that psi down to about 12, and now I can boil water a little over 200 degrees. Because remember, that's what happens if I take a pump that I have in Florida, if I take it up to Denver. Because Denver's called the Mile High City. The Mile High City means it's 5,280 feet. So 5,280 feet. What we're seeing here is about every 2,000 feet you're going to lose 1 pound of pressure. All right? So at 4,000 feet you lose 2 pounds of pressure. Then at 1,000 feet you lose another half a pound of pressure. And finally, the last 280 feet, we're going to call it 0.2. Why? It makes the math easier. Okay, so 2 plus 0.2 plus 0.5 equals 2.7. 2.7 puts us right around 12 psi. Now, notice over here, it says that if I were to lower the pressure over the water to about 1/4 of a pound, I would have boiled water at 70 degrees. So if I can get the water pressure over the water down to 1/4 of a pound, I can boil water at about 70 degrees. Now, this is the vapor pressure point curve. So it takes the chart we looked at and moves it into a curve form, and you can see the vapor pressure point curve starts on the left-hand side there at around 30 to 40, and it goes all the way over to the right-hand side at about 212. Now, the reason for that is because everything below that line is a liquid, everything above that line is a vapor. If I go out to the very end of the line and draw a line right straight down, my guess is going to be 14.7 psi. Go from that point over to the left-hand side, and my guess is 212 degrees. Really close to freezing. Now remember, in Denver, I only have about 12 pounds of pressure, which means I can boil water a little over 200 degrees. And then think about what happens when I get down to 1/2 pound of pressure. I can boil water at almost 70 degrees. Let's take a look at what happens when I actually boil water. Now, of course, what's going to happen? Well, in about 8 to 10 minutes, the water will start doing this. And what we're seeing is we're seeing some vapor bubbles form on the bottom. Some of them are going to break loose, and what are they going to do? Oh, everybody says they're going to float to the surface. Of course they're going to float to the surface. We all know they're going to float to the surface. And I say, really? We really do all know that? I said, I'll tell you what. Answer me this question. Where are we heating the water from? Okay, so when the vapor bubble breaks loose, Will it float to the surface? All right? False. That's false. Because the bottom line is, cooler water is at the top. So when the hot vapor bubble hits the cooler water, it collapses. That collapse lets off a shock wave. Okay? Now once the water gets hot all the way through, now the vapor bubbles go to the surface and they explode instead of imploding down in the water. Now, here's the point. Cavitation occurs in the pump sometimes. When it occurs in the pump, basically what happens is this: we get the water flowing so fast that as it goes through the eye of the impeller, we wind up lowering the pressure. And we lower that pressure to the vapor pressure point of the water, and then once we get that pressure down to the vapor pressure point of the water, we got a problem. But if you look at the impeller, you're going to notice at the eye of the impeller, the area is much smaller than at the peripheral of the impeller. Now, what does it mean? Well, it means that as that area gets larger, according to Bernoulli, there's going to be more pressure. And he's right. So what happens when the vapor bubble, now remember, this is cold water, this isn't hot water. What happens when that vapor bubble gets out to the outside edge? What's going to happen is this. We're going to push that water this way. Remember, we're trying to increase the velocity of the water. Okay? So as the water moves out in that direction, you're going to notice that the vapor bubbles are going to move along with it till they get to a high pressure point and can no longer remain vapor anymore. Then what winds up happening? They collapse, they send out a shock wave, and then that shock wave takes care of destroying the impeller. And it doesn't matter what the material of construction is. Cast iron is the worst. Stainless steel and plastic are probably the best, and bronze is right up there with them. Okay? Now, how do you get the water moving that fast, you say? Easy. Open discharge the pump. Now, of course, if you don't have enough back pressure, what does it mean? It means that that vapor bubble goes all the way through the pump and out. Lucky you. You never see cavitation damage. Okay? So, cavitation damage here, you can see it's inside those two orange circles. And, of course, you can see it ate right through this impeller. This impeller, by the way, is an 18-inch impeller. It is $2,000 list price. And when we told the customer, look, if you would just slow your flow down, you wouldn't have to be buying a new impeller every year. And he says, I don't care. I would rather have the flow. So that's the cavitation damage right there. It can be prevented. That's the important thing to remember. You can always prevent cavitation just by putting more back pressure on the pump. All right? So, Advanced Hydraulics 2, we're going to talk about cavitation in an elbow, the movement of the water through the elbow. Remember what we said, that if you move the water through there, what's going to happen? Well, as you move the water through and you're moving towards that elbow, remember, water has weight, it has momentum, it has velocity, it has pressure pushing it, and it wants to go straight. And then it hits that elbow, and boom. You say, no, you got to turn direction. So the most of the water is going to go up and try and squeeze through that little area on top. Now, what does it mean? It means that the outside edge of the elbow is always going to have a high velocity, therefore lower pressure, whereas the inside edge of the elbow, where there's not so much water, is going to always have a low velocity, therefore a higher pressure. And it doesn't matter what direction the impeller, or excuse me, it doesn't matter what direction the pipe is facing. So if it's facing this way, it could even be facing this way, in which case the outside elbow is the bottom of the pipe. Okay? Or it could be facing in this. It doesn't matter. Whatever way it's facing. Okay? Now, of course, here's what winds up happening. If the water is moving through there so fast and the velocity is so high, the pressure will drop to the point of the vapor pressure point of the water, and you are going to get a cavitation. So you'll get a vapor bubble in there. Now, of course, where does the vapor bubble go? And if you follow along here, you can see it's moving right to the outside edge of the pipe. Why is it moving to the outside edge of the pipe, you might ask? And that's simply because of the fact that I have higher pressure down here pushing it in that direction. All right? Now, what happens when the pressure gets too great? The vapor bubble collapses and you get cavitation damage. And so when you look here, there's your sweeping elbow, all right? And if you look really carefully, that white dot right there in the pipe on this end of the cavitation damage, that's a man in a white shirt. The cavitation pipe here is 50 feet in diameter. The area that it affected, it's 115 feet long, 30 feet wide, and 45 foot deep. That's what he's looking into, a pit that's 45 foot deep. Now, what is it? It's the Arizona Spillway at the Hoover Dam. So, I went to the dam website. I took this picture off the dam website. I'm giving them commission here because they took the picture. But everything I need to explain to you why this cavitation happened is in this picture. So we start out with the fact that there were 4 tunnels drilled when they built the Hoover Dam. The question I always ask is, why did they build the Hoover Dam? And of course, the answer most people give me is, well, electricity, of course. Did you know that in 1934, when they started this project, Las Vegas had a total number of people called 38? They had 38 people in Las Vegas. That was it. So, did they build this dam just for electricity? No, but that was a good byproduct of it. 17 turbines down in the bottom. Lots of electricity. On the other end there is where the water came in at. Now, the reason they built the dam, well, some people say it's because of the fact they wanted to put people to work. I mean, the bottom line is, this is 1934. We're on the latter side of the Great Depression, and people were looking to work. So let's put people to work. It's kind of like what President Obama did in 2008 when everything kind of fell out. He started doing roads because he knew people would be working. If people were work, they would get paid, and if they got paid, they'd spend some of their money, which is how you get a recovery. So let's put people to work. Another reason for putting the dam in, if you take a real close look, there is a tunnel that goes from Lake Mead all the way out to the west coast and to the city of Los Angeles. And Los Angeles buys their water from Lake Mead. And all of those reasons are valid reasons, but they're not the main reason. The main reason why they built the Hoover Dam, 1934, there was something that came up called the Dust Bowl. People were starving. And the bottom line is, the farmers told the president, you know what? If you could control the floodwaters of these waters coming out of this river, we could plant usable crops. But right now we can't, because the water comes out so fast, we never know which way the course of the river is going to go. Remember, this is the Colorado River, and it runs through the Grand Canyon. In the wintertime, a lot of snow builds up on those mountains, and in the spring it all melts, and where does it all go? It goes down into the canyon. And remember Bernoulli's law. The more water I put through a smaller area, the faster that water has to move. And it moves so fast that when it comes out into California, where the canyon finally dissipates, it moves so fast that it would tear that river up every year, and they never knew which way it was going to go. So we've got a win-win-win-win here. So let's build a dam. So they dig these tunnels, 4 of them, 2 on the Arizona side, 2 on the Nevada side, and they say, okay, now let's build a dam between them. So they put a dam over on one end, which forced the water through the tunnels. Then they put a dam on the other end to force the water downstream. That meant that the area between the 2 dams, they could put a pump in there and pump it all out. Okay? Now they can dig down to bedrock and start building the Hoover Dam, and that's what they did. So once you get the dam built, if the purpose of the dam is to stop flooding, you can't let water come over the top of the dam. If water comes over the top of the dam, did you keep from flooding? And the answer is no, you didn't. So to help control the flood water so they wouldn't be so bad, they put in a spillway. One on the Arizona side, one on the Nevada side. And if you look at that spillway, you'll notice that it says 550 feet long, 150 feet wide, 170 feet deep. Okay? Now, here's the biggie. Since we don't want water going over, we're going to let that water go through the spillway. But the question is, how much water is there? Okay, how much water is there that's going to go through the spillway? So, if we look at this next picture coming up, and by the way, what they did was there was a big 90-ton door on the end of each of those tunnels. Once they got the dam built and they didn't need the water to go through the tunnels anymore, they closed those 90-ton doors, that forever sealed that tunnel, and allowed the water to start building up behind the dam. Okay? Now, while the water's building up behind the dam, this takes a little while, by the way. So while the water's building up behind the dam, what do? They dig a tunnel right straight down and connect it to that main tunnel. They put in something called a tunnel plug, which was this sweeping L that we first saw. You notice that in the spillway, they've got those big pylons sticking up. In between those big pylons, there are doors. They're made out of a heavy steel. Okay? They have to use hydraulics to open these doors up. When they open these doors up, they can raise the level of Lake Mead by 9 feet. So let's take a look here. There's the door going up, all right? 9 feet. So over here in the corner, we come back 1 foot from the dam, we go up 1 foot, and we go 1 foot out from the spillway door. 1 cubic foot is 7.5 gallons. The crest of the dam was 1,244 feet. So if the crest of the dam here is 1,244 feet, we take 1,244 times 7.5, that's 9,330 gallons of water. 1 foot high, 1 foot back, 1,244 feet across. Remember, we can raise that 9 feet. So we take 9 times 9,330 and we get 83,970 gallons of water. That's almost 84,000 gallons of water per foot. 1 foot back, 9 feet high, 1,244 feet across. 84,000 gallons of water. Which begs the next question. How much water was behind the dam? So this is a picture of the western United States taken from the Space Shuttle Columbia. This area right here is known as Lake Powell. It's in southern Utah. Okay? Lake Powell has the headwaters for the Colorado River, which runs through the Grand Canyon. Remember, once I build the dam, I now have Lake Mead. Lake Mead is 110 miles long. So I take 5,280 feet times 84,000 gallons per foot times 110 miles, and I get 47,044,800,000 gallons of water. And in 1941, someone thought it was a good idea to close the spillway doors and allow that 47 billion gallons of water to go through a 50-foot tunnel. Can you say straw? All right? Now, the other thing I didn't tell you is from here to here is a 400-foot drop. A 400-foot column of water weighs 180 pounds per square inch. And I have a 50-foot tunnel. That's a lot of square inches and a lot of water. In 2004, I was standing right where that yellow X is on the dam. Okay? And I had met a tour guide there. And so I said to the tour guide, can you help me out a little bit? He said, what's your problem? He said, well, I want to know how did the people that worked at the dam know in 1941 that they had cavitation going on over in that tunnel? And he says, oh, that question, huh? He says, well, the answer is this. There was a photographer standing over there taking pictures of the water coming out over here. Now, from there to over here, how far is that? Well, you're going to notice that the tunnel is 2,200 feet. From the end of the tunnel to the tunnel plug is 22, that's almost a half a mile. Okay? It's 1,244 feet across the crest of the dam, we said, and it's 736 feet from bedrock to the top of the dam. Now, I know the picture doesn't look really great, and when you're sitting here looking at that picture saying, let's see, how far would that be? Bottom line is it's at least a half a mile. It's at least a half a mile. So picture this. You are a photographer. You're taking pictures in 1941 of water coming out of that spillway. And all of a sudden, while you're taking your pictures, you notice something in your camera. You call one of the engineers over and you say to the engineer, where are all those rocks coming from? You know there's no rocks going into the spillway. How come rocks are coming out of it? The engineer realizes immediately that there's a problem. Goes to the control tower and says, we have to stop the experiment. It takes them 4.5 hours to get those spillway doors back up and closed. And in that 4.5 hours, the cavitation damage is 115 feet long, 30 feet wide, 45 foot deep. Now, why am I telling you this story? What does it mean to you? All right? What it means to you is this. About 22 years ago, I got a phone call from a guy, and he said to me, Bill, I don't understand this. He says, I'm using a 70-gallon-a-minute submersible pump to sprinkle with. Okay? He says, but I'm having a problem. Every 3 months, 3 feet from the wellhead, I'm popping a hole in the top of the pipe. Now, I just wanted to say, well, you've got cavitation problems. But I know that if I just say you've got cavitation problems, he's going to say, well, how do I fix it? And I'm going to say, I don't know, because I don't know what's causing the problem. So instead of just saying you've got a cavitation problem, I said to him, what's your flow rate? He says 60 gallons a minute. I'm thinking 60 gallons a minute with a 70-gallon-a-minute pump? No, that's not cavitation. Unless, what's your pipe size? He says 2-inch. Now all I have to do is go to my friction loss chart. I look up 2-inch pipe at 50 gallons a minute or 60 gallons a minute, and my velocity in feet per second, 5.7. If I can be between 5 and 7, and it takes a velocity of over 10 feet per second to cause cavitation, what the heck? This isn't cavitation. There's got to be something he's not telling me. I mean, there just has to be. So I continue to press the conversation till I get to him to say, where's your check valve in the line? And he says, oh, we don't have a check valve in line. And I said, there's no check valve in line? He says, no, there's no check valve in line. I said, you do realize with no check valve in line, every time this pump turns off, all that water is going to go right back down the well. And he says, that's what I want. Now think about this for a minute. If all the water goes right back down into the well, that means that the well is fully recovered every time the pump turns on. So how deep is it from the well exit to the water table? And the guy says, oh, well, it's 10 feet. Now, you can tell by the way he's talking, he has no clue what's going on here. I'm going 10 feet? So we're going to look at a curve, and I'm going to show you how to calculate what the pump is doing based on the conditions that you have. All right? So we have 10 feet. We're going to start out by putting our ruler right across the 600-foot level. Then we're going to start dropping it. Okay? So we go down 500, 400, 300, 200, 100. Now we're going down to 50, but 10 is where we really want. Okay? Now, if you look over on the right-hand side of that curve and you look at what the pump is doing, what do you think that pump is doing at 50 feet? 120 gallons a minute. Don't ask me what the horsepower is. It doesn't matter. It doesn't matter. Even the minimum horsepower is doing 120 gallons a minute. Now remember what we said. If I double my flow, I'm going to double my velocity. Did I find a velocity over 10 feet per second? Yes. Did I find my cavitation problem? Yes. Now there are 4 ways to solve this problem. Okay? Remember, we're trying to sprinkle over here. Put a check valve in. But of course, the guy doesn't want a check valve. All right, fine. I'll get rid of the check valve. Okay, here, how about this? Let's use larger pipe. And then somebody says, you know, that's going to cost a lot of money. I don't care. At least it gets the velocity down there. So if you take that pipe size and you go from 2-inch to 3-inch, you're going to bring that velocity down dramatically. Number 3 answer is, well, what is a sprinkler head? It's really nothing more than a flow restrictor. So what if instead of waiting to the end of the line to put a flow restrictor, what if we put a flow restrictor in right away? Okay. Now the problem is it's got to be under the water. It's got to be under the water. And the reason it's got to be under the water is that when it turns on, it immediately goes to 60 gallons a minute. Otherwise, you're going to have that banging still taking place. Okay? And then the last one, put in a variable frequency drive. So we're going to put a variable frequency drive on. By putting a variable frequency drive on, what we do is we tell the drive, stay at half speed for 1 minute. 1 minute is all the time I need to fill my pipe. Now, of course, remember, at half speed, I'm doing 60 gallons a minute. So, big deal. All right? When you get done with your 1 minute run time and you fill that pipe with water, now you can go ahead and kick in and kick up the pressure, and now I'll have the pressure I need to do the job that I want to do. So we look forward to seeing you on the next webinar. Thank you very much.